Thank you. Hello, everyone, and welcome to my talk on data integrity attestation for autonomous system. So autonomous systems are becoming increasingly popular. Examples of these systems include swarm robotics or drones, or even self-driving autonomous cars. Unfortunately, these systems are vulnerable to attacks that can compromise the privacy and the safety of their users. So the goal of our work is to protect these systems by securing the autonomous devices and their interaction. Remote attestation is a security service that allows to ensure or to verify the trustworthiness of a remote device. It is usually established. Okay, this click is not working. It's usually established as an interactive protocol between a trusted party denoted by the verifier and a remote, possibly compromised party denoted by the prover. The verifier is interested in attesting the trustworthiness of the prover. It does this by sending a challenge, typically a nonce. On the prover device, on the other hand, a trusted component, usually realized in hardware, measures the software, computes the hash of the software usually, and sends an authenticated response to the verifier, which checks the response in a database and determines whether the prover is in a trustworthy state. However, static attestation schemes are incapable of detecting runtime attacks, and this is another way to compromise an autonomous system. A short background on runtime attacks. So we classify in this slide runtime attacks into two classes: control flow attacks and control data attacks or non-control data attacks. So if we look at the software of a device, it can be seen as a graph, a control flow graph, where a node in the graph represents a basic block, and an edge represents a control flow event from one block to the other. An adversary may exploit a bug or a vulnerability in a program to change a control flow event or a control flow variable, like an address of a jump or a return instruction of a function, a return address for a function, to jump to his injected code. However, this is usually prevented by data execution prevention, or to jump to a different part of the code, and this is code reuse attack. And this is a prominent example of code reuse attack is return-oriented programming attack. On the other hand, in non-control data attack, the adversary actually changes a data variable rather than a control variable to change the control flow of a program to another legitimate control, but not intended control. For example, the adversary may change a permission or a privilege condition to make the program execute a more privileged execution than it was expected to. So recently, control flow attestation has been proposed in order to detect such attacks. So in short, control flow attestation modifies or changes over the existing attestation by actually not hashing the software, but rather hashing the execution of the software. So it hashes the events. So it uses a cumulative hash and hashes the control flow events of the software. So here in the graph, you see if the basic block A is executed, the hash hashes the block A or the address of block A, and then when you jump to block B, the hash is incremented with the address of block B, and so on. So for ABC, you have the hashes, or for a different ABED, ABEF, you will have a different hash which presents the execution path of the software, not the exact instruction of the software. However, there are multiple problems with the control flow attestation. The first problem, it has a really high overhead on the verifier, which is required to search, to maintain and search a very large database of expected execution paths. So if you have a big program, you'll have an even bigger execution path. And this is, the other problem is it is too complex, especially in the presence of loops or nested loops and recursion in the program. And for this reason, control flow attestation has been so far only applicable to only small programs like a couple of thousand lines of codes or so on. So our actual challenge is how to apply control flow attestation for autonomous systems which have really more complex software. So the high-level idea or the high-level solution is to actually change what we attest, or to answer these three questions. What do we actually attest? When do we actually attest it? And how do we attest it? And this translates to the three basic blocks of our solution, which is modular attestation, data integrity attestation, and execution path representation. So for modular attestation, we actually divide or assume the software is divided into multiple modules that are isolated, and we only attest the modules that are relevant for our use case. So we call these modules critical modules. We attest only when two devices in the autonomous system interact. So when a device actually asks another device for data, we identify the critical modules and only attest these modules. And for the attestation, we use multi-set hash function. Instead of attesting the execution path, we actually attest a multi-set of the executed edges inside the path. So the modular attestation or modularization actually translates to the assumptions of our solution. So we assume the software is modular. The interaction between the modules is done through a clear or well-defined communication channel. And these modules are strongly isolated based on the underlying security architecture. The data flow attestation is done by a component of our solution that we call DF monitor. And the execution path representation is done by the CF monitor, another main component that I will explain in the implementation section. So again, the high-level idea, you have multiple interacting devices. If a device wants the data from another device, it sends a data request. On the other device, multiple modules execute. The DF monitor monitors the execution between these modules and identifies those critical modules that should be attested. And at this point, the CF monitor is activated, and inside each of these modules, it identifies or monitors the execution path of these modules. Then the execution path is then authenticated and reported back with the generated data. We implemented our solution in a recent open hardware for autonomous drone, which is Pixhawk with the PX4 flight controller software. So a little bit more about the PX4 architecture. You have the real-time operating system. On top of the operating system, we have the flight or the middleware, which is formed of two components in addition to other components that are not relevant to our implementation. The Mavlink protocol, which is responsible for the communication to the outside world, and the UORB, which is responsible for the communication between software modules inside the device using so-called publisher-subscriber design. And the flight stack, which is responsible for controlling the drone. The flight stack has the software modules that do the control of the drones. If a module wants to communicate to another module, or one module register at the UORB as a publisher for a type of data, and any other module that is interested in receiving this data also registers as a subscriber for this type of data. And then when this data is available, the middleware notifies the other module that the data is available. So for the DF monitor functionality, we actually need the objective of the DF monitor is to identify those critical modules that influence the generation of the data that we care about. So the data that is exchanged between the devices for their interaction. This is realized by actually modifying the UORB to monitor and record the interaction between modules and thus identify those modules. So we had to add 3 functionality to the middleware. Actually, we had to extend the mavling to allow attestation. We had to extend the UORB to record the messages exchanged between modules, and we had to flush existing data from the communication channel. So simply, the mavling is extended with the 1 bit that identifies whether the data exchange should be attested, and with the field for the attestation result. The UORB buffers, so since the UORB is asynchronous, so all data might be found before the request of data, so the buffers should be flushed so that you ensure that you attest all the generated data. And finally, the registering of data or the generation of data is recorded by the DF monitor so that we can identify the critical modules. The CF monitor, on the other hand, aims at detecting the control flow of those critical modules. It is realized by instrumenting all modules on the device so that they can run the logic that's responsible for measuring the control flow. And it has 2 main functionality, a logic that actually calculates the multiset hash function and measures the control flow, and an instrumentation that actually calls this logic on every control flow event. So if you have these 6 modules, module 1, 3, and 5 are the critical one. The CF monitor stores 1 table for the ID of the critical modules. This table is maintained by the DF monitor, which actually detects these modules and forwards them to the CF monitor. For each module, the CF monitor also stores the multiset hash value, or the value of the hash of the multiset of the edges that were executed, and the actual multiset of the executed path. So for example, when in the module M1, the path is executed, the logic of the CF monitor stores the multiset that represents this executed path. So for example, edge 1 is executed once, edge E1 is executed once, edge E2 is executed once, and E4 also once. The same for M3. To see this in more detail, so if edge E1 is executed, our instrumentation forwards for the CF monitor 2 attributes: the ID of the module that is executing and the ID of the edge that executes. The CF monitor logic then checks the ID in the critical modules. If it exists, it modifies the multiset hash value for this ID and also updates the execution path multiset accordingly. So for E1, similarly, when E2 is executed and when E3, and if an edge is executed that is already in the path, it only updates the number of times that this edge has been executed. So we integrated our implementation into the PX4. The DF monitor is integrated simply by modifying the UORB, as I said, to intercept every communication between modules and record this communication. The DF monitor, on the other hand, is the instrumentation from modules that jump to a logic that calculates a multiset hash function. In addition to this, we needed a filter to filter the data coming or the attestation requests coming in order not to alter with the internal state of the PX4, and a coder that actually signs the attestation or authenticates the attestation response with the data when it's generated. So we evaluated our solution to assess the overall gain from using modularity. We evaluated the case where devices exchange GPS coordinates. We realized that so a device one device requests GPS coordinates from another device, and this table here shows for all the executing modules the CFG size, the execution path, the attestation time, and the verification time. And what we can see from this table is that when GPS location is actually generated, 13 modules are executed, and only one of these modules is actually critical for the generation of the GPS data. It's actually influencing the value of the GPS data. So this gives us a saving of actually 95% on runtime when running the control flow attestation for the whole device. Of course, the GPS coordinates were the extreme case where we get the most gain. For this, we evaluated other data that can be generated by a drone. And for each of these data, we measured the count, the sum of the executing, the sum of CFGs, the sum of executed paths for both critical and executed modules. And we also show the percentage critical versus executed. For example, for the accelerometer sensor, you can see that 2 out of 7 executed modules are only critical for this sensor data, which is 28%. And the CFG size of critical module is like 12% of the CFG size of all the modules that were executing when this data was generated. Similarly, the execution path is 24% of the overall execution path. For scalability, or to measure the scalability, we simulated our solution for larger interactions. We considered multiple scenarios where devices interact, sharing their GPS positions sequentially, in parallel, or in a hybrid way, sequentially and in parallel. We considered 3 scenarios: normal collaboration, devices only recursively exchange GPS, authentication, where the GPS is authenticated with the elliptic curve DSA, and our solution, the runtime in the serial is linear for the 3 cases, and the parallel is constant for the control scenario and linear for the other 2 cases. And the most interesting is the hybrid scenario, where we can see that the runtime is logarithmic in the number of collaborating devices, and that imposes only 4x times the normal authentication while providing more integrity of the exchange data. So last but not least, of course, the security. Since DF Monitor has an overall or a full overview of the communication, it could detect all critical modules, so the attacker can't actually change the data with a module that is not attested. The CF Monitor can detect any edges or any execution or any jumps that are not in the CFG, for example, return-oriented programming attacks. Any jumps in the CFG to be detected, this go back to the policy. So if the attacker wants to execute a more privileged edge, and we know about this edge, this will be detected. However, if the attacker only reorders the edges in the multiset, this wouldn't be, of course, detected, because we use a multiset to report the execution path. In conclusion, there are 3 things that I want you to take away. Static attestation cannot detect runtime attacks. Control flow attestation is promising for detecting such attack. However, it's too complex. In order to apply this for autonomous system, we really need to consider designing modular software for this system and designing hardware architecture that provide strong isolation. Thank you for your attention. With this, I would like to take your questions. One quick question we have time for?
So, Virgil Gligor, Carnegie Mellon, very nice work.
Thank you.
I have a question about how do you handle asynchronous events like interrupts that change control flow, traps, breakpoints, and the like?
Yeah, so on the current talk, we assume that these are disabled, but we are working on a hardware solution where we could handle these.
The problem is that you have to prove that they are disabled. In other words, a disable instruction in memory doesn't mean that interrupts are disabled because it can be skipped. So
Yep.
future work, huh?
Yeah,
Okay, very good, thanks.
thank you.
Let's thank the speaker again.